All right, here we're going to look at some functions and try to figure out where are they discontinuous at and what type of discontinuity it is, whether it's removable, jump, or infinite. So the first thing we need to remember is what are the things that tell us if a function is discontinuous. And so if we go back to our notes, which I haven't cleared from my last video, there's three things, right? F of x is not defined. The limit of x, sorry, the limit as x approaches some value doesn't exist. And the limit as x approaches some value of f of x has to equal f of that value. So if any of those three is a problem, that's going to be where we're discontinuous. So we need to keep that in mind while we're looking at these. So here, what I see immediately is that we have a domain issue. There's some value that is not in the domain of x. And whatever's going to make that denominator 0 is not going to be in the domain of x. So I know that this x right here can't be -3. I know that f of negative, oops, let's try that again. F of -3 is not defined. And so what that tells me is it's going to be discontinuous at x is equal to -3. So we know that that's probably going to be the case because it doesn't fit the first criteria for being continuous at that point. So it's not defined. So we're done. Now what we need to do is look at the limit. Can we determine what the limit is as x approaches -3 of x squared plus 3x over x plus 3? Well, we need to use the stuff that we learned in the last chapter in order to see if we can evaluate this limit. Now, we can't just plug it in. It's a rational function, but if we plug in a -3, that denominator is going to be 0. Can't do that. So what we're going to do is see if we can come up with an equivalent function, right? So if we try to factor that numerator, hopefully y'all are all getting better at seeing these. Then notice we'll have x times x plus 3. Factor an x out of both of those terms. We have an x plus 3 here. And so that x plus 3 and that x plus 3 can reduce. And so what we're left with is the limit as x approaches -3 of just x. Just going to equal -3. And so since the limit is defined, it's approaching the same value from both sides, but it's just not the function is not defined at value. That means that it is a removable discontinuity. At x, well, it's a very bad at sign, so let's just write out the word. At x equals -3. What that means is that if we define this function f of x such that it was this most of the time, but when x is equal to -3, we defined it as just being -3. We just changed that definition for that one value for the function. Boom, it would be continuous. And so that's why it's a removable discontinuity at x is equal to -3. Let's look at another one. Here we have a piecewise defined function. Piecewise defined functions are pretty nice because they're kind of easy to spot where the problem might happen. Well, the definition of this function is -1 when x is less than or equal to 3, and it's -x minus 1 when x is greater than 3. So that switch in definition is happening at x is equal to 3. So I think my problem is going to happen at x is equal to 3. I think it's going to be discontinuous at x equals 3. Now, is it defined? What is f of 3? Well, when x is 3, I'm going to use this top portion here, this top piece here. And so f of 3 is just going to be -1. So it's defined. Good. Let's see if we can find the limit. Well, we're trying to find the limit as x approaches 3 of f of x. But there's a problem. It's defined differently on the left side of 3. It's defined differently on the right side of 3. So let's break it up. Let's look at each one. So let's do the limit as x approaches 3 from the left of f of x. And let's see what that is. Well, when we're from the left of 3, we're talking about values that are less than 3. When we're talking about values that are less than 3, we're talking about this definition of the function there. So this is going to be the limit as x approaches negative, 3 from the left of -1. That is the definition of that function there. And so that is just going to equal, well, it's a constant, -1, so it's going to be -1. Let's take a look at the right side limit. So we're talking about a limit as x approaches 3 from the right of f of x. Well, when it's on the right of 3, we're going to use this piece here because we're talking about values that are greater than 3. So this is going to be the limit as x approaches 3 from the right of -x minus 1. And so that's going to equal -3 minus 1, which is going to be -4. So the limit from the left is -1. The limit from the right is -4. That means the limit as x approaches 3 of f of x does not exist. There's a jump happening. From the left, it's going to -1. From the right, it's going to -4. There's a jump happening. It's not going to positive or negative infinity. So what do you think it is? It's a jump discontinuity at x is equal to 3. And let's look at one more. Here we have f of x is equal to x plus 2 divided by x squared minus x minus 6. Well, initially I look at this and I go, oh, we got domain issues possibly, right? And so what I'm gonna try to do, I want to factor this denominator at the off the bat. I just want to see what it looks like, see what can make that 0, and it's gonna be useful down the road probably. So why not? So if we factor this x squared minus x minus 6, that's gonna be x plus 2 times x minus 3. So I'm going to have problems at x equals -2 and x equals 3. So we're going to have 2 discontinuity places here. I know that because it's not defined for -2, it's not defined for 3, because both of those will cause that denominator to be 0. So let's take a look at each one. First, let's look at the -2. So it's not defined for that, but let's see if we can find the limit. If we can find a limit and it's not going to positive negative infinity, it's going to be a jump discontinuity. So let's see. So let's try to, well, let's do a different color, huh? So let's go with blue for 2. So we'll do the limit as x approaches -2 of x plus 2. I'm going to use the factored form because it's it's going to be easy to work with. And x minus 3. And so we can't plug in the -2 there because that denominator is going to go to 0, but we can reduce. But boom, x plus 2 and x plus 2. And so what we're left with after that is the limit as x approaches -2 of 1 divided by x minus 3. That we can work with. It's a rational function. It's an equivalent function of what we started with. And we can actually plug in the -2 there. And so this is going to give me 1 over -2 minus 3, which is 1 over -5. So the limit exists. That means that it's approaching the same value from the left and the right, but boom, at the value it's not defined. And so that means it's going to be a removable discontinuity at x equals -2. That does not mean anything about the 3. So we need to look at the 3 separate. So let's do that. So let's rewrite our function. First off, and let's go with green or something. So remember the function was f of x is equal to x plus 2, I believe. Let me make sure on that. Yep. Divided by x plus 2. I'm going to keep using the factored form because it's just easier to work with. X minus 3, and my x looks like a backwards alpha, so let me fix that. All right, so we know it's not defined at x equals 3, but can we find a limit? Well, let's see. We try to do the limit as x approaches 3 of x plus 2 divided by x plus 2 times x minus 3. I can't reduce anything, and that denominator is going to go to 0 even if I just take the limit of it. So that's not going to work. I can't do anything. So you could go with the table structure here to try to figure out what's happening. I like to just kind of think through it logically. So what I want to do is I want to look at it from the left and the right. So let's go ahead. Let's go with blue for the left. Let's do limit as x approaches 3 from the left of x plus 2 over x plus 2 times x minus 3. Okay. And so the x plus 2, I mean, that's going to go to 5, right? Well, let's give myself some room. Let me rewrite the limit. So we're going to limit as x approaches 3 from the left. But that numerator is going to go to 5. This x plus 2 here is going to also go to 5. But what's going to happen with that x minus 3? Let's keep that written for right now. And let's think about what's going to happen. So what we're doing is we're taking a number that's very close to 3, but less than it. It's on the left side, and we're plugging it in here. And so when you take a number that's very close to 3, but less than 3, and subtract 3 from it, what you're going to end up with here is a small negative number there, right? And so if I take 5 and I divide it by a very tiny negative number, where's that going to go to? Negative infinity. Okay. Now, if you did the table, you would see that, hopefully see that trend as well. From the left side, it's going to grow further and further from 0, but in the negative sense. Now let's look from the right. Do I have room here? Yeah, I do. Let's go with red. So we're talking about the limit as x approaches 3 from the right of x plus 2 divided by x plus 2 and x minus 3. And honestly, you could reduce the x plus 2's here to work out, because I mean the 5 and the 5 were reduced, right? So let's go ahead and do that this time. Actually, let's get rid of that. Boom. And so what we end up with is the limit as x approaches 3 from the right of 1 over x minus 3. And so what's going to happen here? Well, we're looking at a number that's slightly larger than 3, because it's approaching 3 from the right, and we're plugging that into that x there. And so we're taking a number that's slightly larger than 3 and subtracting 3 from it. What we're going to end up with is a very small positive number. And so whenever we do that, 1 divided by a small positive number is going to go to either positive or negative infinity. But since it's positive, it's going to go to positive infinity. And so since these limits aren't equal to each other, and when one side is going to, well, actually it's going to positive infinity here, it's going to negative infinity. Let's try that again. It's going to negative infinity here. What kind of discontinuity is going to be? It's going to be an infinite discontinuity. At x is equal to 3. So for this function that we were looking at, we got it written out here, but it's in the factored form. Looking at that function there at, I think it was 2, was it? Yep. Oh, at -2. It's a removable discontinuity at x is equal to -2, and it's an infinite discontinuity at x is equal to 3. All right, and that's it for some examples.